All right, let me give you a little bit of help on some of these relativity homework problems. We're going to take the problems that you can see here on the page in front of us, and I'll give you the diagrams. I mean, we did number 1 here in homework handout, relativity handout number 1. I think this is homework 23. We did that in class. I'm not going to do that anymore. We'll do 2, 3, 4, and 5. Okay, and we'll see. Just give you the setup. I'll just give you the diagrams to get you started, so that it hopefully won't be quite so bad. So let's take a look here. In problem 2, we have an object that has a length of 8 nanoseconds, is measured in a frame of reference, in which an object is at rest. What speed would an observer in a moving reference frame have to have in order for them to measure the object with a length that's half as much, or 4 nanoseconds? We did this in class too, but I'll just do the setup again real quick. So we're going to use the sketch diagrams because we don't have a particular speed, because we don't know beta, so we can't do that. So we're just going to have our sketch diagram. That's what I would encourage you to use. And again, I would encourage you to do the sketches big, not small. And I would encourage you to do them in a PowerPoint or something with straight lines and a ruler, instead of trying to just do it all freehand. You're trying to see patterns, and if it's too sloppy, you're not going to see any patterns. So anyway, we have an object which has a length. So the idea is, when we're measuring the length of an object, we have to have 2 world lines. Here's one world line for the object. Here's the other world line. One is for the front of the object, one is for the back of the object. And context is arbitrary, so I've chosen to make this object stationary in the perpendicular reference frame. Remember, when the world line is parallel to the time axis, that means the object is stationary in that reference frame. These world lines are both parallel to the TS axis, and so the object is stationary in the perpendicular reference frame. And we're told that the distance, the length, the distance between the front and the back is 8 nanoseconds, and that's being measured in the frame of reference where the object is at rest, which means it's in the perpendicular, and the distance measured in the perpendicular reference frame is a delta XS. What we want to do is put some tape down. The person measuring this object in the reference frame where it's moving would have to put tape down on the front and the back world lines simultaneously. And we've done that example in class. When somebody's measuring something that's moving past them, they have to mark the front and the back simultaneously with pieces of tape, and then they measure the distance between the pieces of tape. And we're told that we want this distance to be half the length in the perpendicular reference frame, and this is a delta XM because this is the skewed reference frame. And the question in this problem is, what's the beta that makes that happen? And hopefully what you can see by the diagram, and again, what we're looking at here are the 2 dots. These are the things I'm keying in on when I make the following statement. The position of these 2 dots, both of them on a line that's parallel to the XM axis, actually on the XM axis. It could also be on any line parallel to the XM axis. When that happens, then that means those two events occurred simultaneously, or that means that delta T measured in this case in the skewed reference frame is 0. That's what simultaneous means. There's no time between the two events. And the two events are the dots, the blue dots. That gives us a simplified Lorentz equation of delta xs equals gamma delta xm. And I'm trying to get beta, and beta's not in here anywhere. Well, do what you can. Let's solve this for gamma. So we do some algebra. Algebra gives gamma equals delta xs over delta xm, which is 2. I've got 8 nanoseconds and divided by 4 nanoseconds, that's 2. Well, if we remember, gamma is related to beta. So I need to solve that equation for beta. For gamma now, we know gamma is 2. So that's that problem, okay? That's that problem. Let's go back to the sheet. Problem 3 says an observer in a reference frame moving at a speed of 1/3 sees 2 events occur, event A and event B, and it gives coordinates for those. And it wants to know what the coordinates are for the events in the stationary reference frame. So we're looking at this problem. We see a beta of 1/3. There's a reference frame moving at a speed of 1/3. There's an observer in that reference frame, and they're making measurements. Okay, they see 2 events, and they give measurements or coordinates for those events. So there's an observer making measurements, and the definition of beta is the dimensionless velocity of the moving observer. So we're going to go back to our diagram. We're going to choose the beta 1/3 diagram. There we are. Okay. So we have a special graph, and if you have a special graph, it's best to use it. So there's our graph, and we have 2 events. So let's take a look at the 2 events. 2 events are event A is 2-3. Time distance is 2-3. So let's go put a dot here at 2-3. 2 in time. So there's 1, there's 2, and 3 in distance. 1, 2, 3. And where those intersect, that's where I put my dot. That's event A. In the skewed reference frame, see how I've drawn the lines? They're parallel to the skewed axis lines. I can't stress enough how drawing the lines and making things parallel in the right reference frame, just making these constructions, can help this whole process for you. Then we have event B. And event B is 7 seconds in time and 3 seconds in distance. So it's 7-3. So let's go back here. So there's 2 in time, there's 3 in time, 4, 5, 6, 7, and I go out. And I'm still at 3 in distance, and where those intersect, I draw a dot, that's B. And I have the coordinates. This is 2, 3, and this is T, M, and X, M. And this is 7, 3, and this is T, M, and X, M. And now we can answer all the questions. There are various questions about distances between dots and in different reference frames and all the rest. Notice something here. Notice something here. Delta X M. Well, I'm not going to tell you that. I'm just going to leave it alone. Some of the questions that are given you are asking you to compare each dot with the other, comparing A and B, the distance between A and B, the time between A and B. Other questions are asking you for the coordinates of event A. Well, coordinates always mean you're comparing the dot with the origin. So the position coordinate would be how far A is from the origin. The coordinate for B would be how far B is from the origin in time and distance. So a coordinate, when the term coordinate is used, you're comparing the dot in question with the origin. In some of the questions in the homework, you're asked to compare each dot with the other dot. So you just have to read the questions carefully. And you'll have to do transformation calculations. But look, you can do a rough guesstimate here of the coordinates for B in the perpendicular reference frame. If I wanted to do that, I would draw lines now parallel to perpendicular grid lines. And you should hopefully be able to see where B is in time in the perpendicular reference frame. It's at 1, 2, 3, 4, 5, 6, 7, about 8 1/3. And in position, it's 1, 2, 3, 4, 5, 5 3/4. Okay, so you can get a rough estimate. But again, the idea is to draw lines that can help you to read the grids, and the lines have to be parallel to the right axes so that you're making measurements in the correct reference frame. I know it gets a little busy, but anyway, you can read these numbers from the graph. That's an approximation, and when you calculate using the Lorentz equations, you should be able to get more precise, but they should be close. Your approximate eyeball reading of the graph should be close to what you get when you do the detailed calculations. All right, let's take a look at two spaceships are playing a little game of chicken. One spaceship is facing left and the other is moving past at a speed of 3/5 the speed of light. They're both 100 nanoseconds long as measured by somebody in the frame where the ships are at rest. And then we're going to fire a cannon and blah, blah, blah. So here we go. Let's try and make some kind of a diagram for this. So we're going to go back and we're going to pick the diagram for 3/5. There's 1/2, there's 3/5 right there. We have two spaceships. One is in the perpendicular reference frame. And it's 100 nanoseconds long in the frame of reference where it's at rest. So in the perpendicular reference frame, I know that this delta XS from here to here, between the front and the back world lines, is 100 nanoseconds. I also have a spaceship that is in the frame of reference 1, 1, 2, 3, 4, 5. And I know that this distance from here to here, between the front and the back, as measured in the skewed reference frame, that's also 100 nanoseconds. Both ships are the same length in a frame of reference where they're at rest. And so here's the diagram of the two spaceships. At the moment when the two spaceships are passing nose to tail, okay, so this is the nose of one spaceship. This is the tail of that spaceship. This is the nose of the spaceship going right. This is the tail of the spaceship going right. Okay? When the nose and the tail are lined up, at that instant, simultaneously with that, the captain fires a cannon that's located at the tail of his ship. This is the ship that's sitting still in the frame, in the perpendicular reference frame. So there's a cannon that gets fired. So this dot right here represents the event of the nose and tail of the two ships passing each other. This dot here represents the event of firing the cannon. And the question is whether the ships hit, the cannon hits the other ship. And so you have to, I'm going to encourage you to extend this line so that it comes down here someplace, and then you have to interpret. So there's the diagram for you. Maybe that'll give you a little help. Then we have a problem where we have some information given about spaceships flying, and let's see, what's some information here we can pick? We can say that there's a spaceship flying at 1/5, there's a spaceship flying at 3/4, and then there is a race commissioner flies by at a speed of 2/3, and he's making a measurement. How long is the ribbon measured by the commissioner? So the commissioner is making a measurement. He's an observer. His velocity is 2/3. So he needs to be the moving observer. So here we go. We have to get our 2/3 diagram. There's our 2/3 diagram. Beta is 2/3. So this is the correct diagram. The race commissioner is in the skewed reference frame. This is the space commissioner's reference frame. It's the grid he uses to make measurements. The other measurements of velocity are measured by somebody in the perpendicular reference frame. Let's say that's the Earth. And we're told some spaceships fly and carry the ends of a ribbon for a race. Okay? And those velocities that are given, the 1/5 and the 3/4, those spaceships are doing something, but they're not observing. They're not observers. Nobody in those spaceships is making an observation or a measurement. So their velocities are not betas. Remember, beta is the dimensionless velocity of the moving observer. The moving observer here is the race commissioner, and he's flying at 2/3 the speed of light. That's this reference frame. So that's why we picked this diagram and not another one. There is a spaceship that flies at 1/5 the speed of light for 5 seconds. Well, let's say they start at the origin and they're going to fly for 5 seconds. One, 2, 3, 4, 5. And they're flying at 1/5 the speed of light. So that means that's a velocity. That's the inverse of the slope. So the slope is 5. So if I have a 5 rise, I'm going to have a run of 1. Okay. And after that, after they fly for the 1/5 the speed of light for 5 seconds, they stop. And then the world line goes like this, because a world line that's parallel to a time axis means it's stationary in that frame of reference. And the perpendicular observer is telling us they flew at 1/5 the speed of light for 5 seconds and then stopped. So we draw these things in that frame of reference. Then we have another piece of information that says we flew at 3/4 the speed of light for 8 seconds. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. This is the diagram for the spaceship flying at 3/4 the speed of light for 8 seconds. So this world line was flying for 8 seconds. Here's 1, 2, 3, 4, 5, 6, 7, 8. Okay, right to there. And they're flying at 3/4 the speed of light, so that means the slope of this line has got to be 4/3 or 8/6. Right? The slope is 4/3. If I double the numerator and the denominator, I don't change the fraction, but I get 8/6. That means the run is 6. The rise is 8. Well, I already know this is a rise of 8. I need a run of 6. 1, 2, 3, 4, 5, 6. And so there's the point at which it arrives after 8 seconds. And then it stops. And so again, we have a world line that goes parallel to the TS axis. And the tape for the race is carried by each of these spaceships, and one end is carried by one and one end is carried by the other. And so now we're going to make our diagram I'm just going to extend these world lines. Okay, and I would encourage you to, to keep things simple. Okay, anyway, I'm just going to extend those world lines because it's the distance between these two world lines that I'm trying to measure. And in the perpendicular reference frame, that's a pretty easy thing to do. I can just measure the distance between here and here. That's a delta XS, and that's pretty simple here. It's 1, 2, 3, 4, 5. This is 5 seconds. There's 5 seconds in distance between the front and the back end of the finish line tape. And now I'm asking, what does the race commissioner say the length of the tape is? Well, he sees the tape moving past him. He has to measure it by putting tape down simultaneously. One at this tape, the thing he's trying to measure, and one at this tape, the other end of the thing he's trying to measure, at the same instant in time, so they're both on the TM axis at the same time. I'm sorry, the XM axis. This is delta XM. Okay. And if I look at those two dots tell me that delta TM equals 0, which gives me a Lorentz equation that says, well, I'll let you figure out which equation to use. I've just told you the most important thing. Delta TM is 0. And here's the diagram that helps you figure it out. And we can actually make a guess as to the answer, because if we look, there's a line here through that dot, there's a line here through that dot, and the distance between those lines is, here's 1, 2, 3, 3 1/3, and another third, and 3 2/3, 3.6, 3.7. So it looks like it's approximately 3.7 seconds. When you do the actual calculation, you should come out to something like that, 3.5, somewhere between 3.5 and 4 seconds. Okay? That's an approximation. You should do it more carefully using the Lorentz equations. Okay. Here's the last homework. So let me just do these real quick for you. Yeah.
Hey, Aaron asked me if I could offer extra credit for the home.
All right. So here's a problem on the last relativity homework handout 3. This is homework 25, I believe. A person commutes to work 50 miles one way and 50 miles back. That's 100 miles a day. For 250 days a year, for 35 years. During the commute, the person drives at a speed of 65 miles per hour as measured by someone who's stationary relative to the car. That means the beta, the person in the car, is also going to make a measurement. And so they have a velocity, and so their velocity is the beta, and the velocity is 65 miles per hour, but you have to make it dimensionless because beta is dimensionless, so you have to divide by c. So you need to convert the 65 miles per hour to meters per second and then divide by c to get the beta, and this is going to give us a small beta. Okay. And the time that's going to be measured by that person is the watch that they're wearing. Okay. And that watch will measure different time because it's moving relative to, say, a clock on the person's mantelpiece at home. We want to know how much do the two clocks differ because of relativity. Okay, so let's make a diagram of this. All right, this is clearly going to be a sketch. We don't have a special diagram for such a low velocity. So here, here's a sketch diagram. And so we have the car and the person driving in the car. There are two events that are going to be represented. First of all, this is the person commuting in the car. We'll think of it as just one big long trip, okay? To make the diagram simple, instead of turning around and coming home and going back the other day, and we'll just keep it simple. There's where he starts his commute, and let's say this is where he ends his commute. And notice that the two dots, the event dots, are on the TM axis line because the person who's commuting is in his own reference frame, the reference frame of the car, and the commute occurs in that reference frame. So the starting and the stopping is going to be in that reference frame. And if we wanted to measure, it's the person in the perpendicular reference frame who's measuring the time of this commute, right? How much time there is in the commute. And that's here. That's a delta TS, okay? And that's going to be measured by the clock that's stationary, say the watch or the clock at the guy's home. It's not moving, it's stationary. This time from here to here, that's a delta TM. That's the time for the commuting as measured by the person who's driving the car. Okay. Now, here's what we know. We know that here's where we're going to do a little dimensional analysis. Okay, a little dimensional analysis. We have 65 miles per hour. We also have the distance that was traveled. We have 100 miles per day times 250 days per year times 365 let's see, 250 days per year. Here we go. Right, so let me do this. The days and the days cancel, right? Oh, times 35 years. So they cancel. And we're left with, that'll give us how many miles the total trip is. Okay, that'll give us the total miles. And then we have, and let's call this, we'll call this big D. That's the distance, okay, in miles. D miles. So if I do a little dimensional analysis again, I'm going to say D miles times fraction 65 miles per hour these miles and miles will cancel, and then I have that's how many hours, and then we have 1 hour is 60 seconds, and I get so this would give me the time in seconds. That's the time in seconds. And that's a time as measured by somebody who's measuring the 65 miles per hour. So that's over here. This is my TS. That's the time as measured by somebody in the perpendicular reference frame. And again, we have here delta xm equals 0. Because if I look at these two dots, they occur on this axis line. Come on in. So this will give you the simplified Lorentz equation to use. And you should be able to solve for this delta Tm. And then the question is asking you for the difference between this time and this time. How different are they? So you're going to have to subtract those two. And again, you need to use a calculator that's going to be very precise because this is a very low speed beta. And remember, I have to divide by c in order to make it a beta, dimensionless. So I need to convert this to meters per second so I can have divide by c in meters per second. And so that will give you the answer to that problem. And then let's take a look at the other one here. Okay, spaceship leaves Earth, flies to Alpha Centauri, 4.3 light years distance, and returns, and it's like 9 years later, as measured by the clocks on Earth. Assume the ship is K-smart. Okay, so again, this is a commuting problem. It's just like number one. So let's do a similar setup. I'm just going to make a sketch here because it's going to be a sketch. Here's the perpendicular reference frame. Here's the skewed reference frame. We have spaceship flying. We're told that it leaves and returns, and the time between those two events is measured by somebody in the perpendicular reference frame. So this is delta TS. This is 9 years. And we're told that the distance it leaves and returns, this is, pull that back up here. This is a delta XS, and this is going to be 8.6 years. How do I know that? Because I was told the distance is 4.3 light years, and it went and returned 8.6 years. So the velocity beta is the velocity. That's the inverse of the slope. And the slope is rise over run. Right? So the beta is going to be delta XS over delta TS. You should be able to figure that out. Again, The two dots tell me that delta xm equals 0. The astronauts have not traveled anywhere in their own frame of reference, in the reference in the spaceship. That should allow you to convert this time here. Let's see, what are we asking now? How much time has passed in the skewed reference frame? This is delta Tm. That's the question. How much time passed for the travelers on the spaceship? And this is the story of the Planet of the Apes. Travelers go out from the spaceship and fly for quite a long distance at a high rate of speed, and they come back, and their clocks have only ticked by a couple of years, but on Earth much more time has gone by. And all clocks tick differently in relativity theory. Biological clocks tick differently as well as mechanical clocks. So that would be the diagram for problem 2. And then problem 3, 3/5 the speed of light. Let's take a look. There, 3/5 the speed of light. This is a messy diagram, but we'll use it anyway. We have our moving observer moving to the right at 3/5 the speed of light. This diagram has a beta of 3/5. And we have someone flying to the left at 3/5 the speed of light. Right? The problem says that at 3/5 the speed of light, ships are observed traveling in opposite directions. And they're both traveling at 3/5 the speed of light. One is going to the right, one is going to the left. So I'm going to go and 3/5. So that's 5. That's 1, 2. No, that's not what I wanted to do. Do that. Okay. That's not what I wanted to do again. There we go. 1, 1, 2, 3, 4, 5. 1, 2, 3. Okay. So there's a ship flying to the left, one flying to the right, and we want to measure the velocity of this ship as measured by this observer. I have an event dot here, and I have an event dot here. The perpendicular observer tells me the speeds are 3/5, so we can see from here to here between the two dots. This is a delta TS, and that's 1, 2, 3, 4, 5. That's 5 seconds. And between here and here, between the two dots, this is the run between the two dots. This is delta XS. It's minus 3 seconds. You convert those to a delta TM and a delta XM in the skewed reference frame. So use the Lorentz equations. To find delta xm, which is the run, delta tm, which is the rise, then calculate velocity equals delta xm divided by delta tm, inverse slope, and that should give you that. So those are the setups for the homework problems. Hopefully that's helpful for you.